Hey there, it's Shannon Myers, and today we are checking out diagonalization. So let's start off with the definition. Definition of diagonalizable matrix. An n by n matrix A is diagonalizable when A is similar to a diagonal matrix. That is, A is diagonalizable when there exists an invertible matrix P such that P inverse times A times P is a diagonal matrix. So the first theorem talks about the fact that similar matrices have the same eigenvalues, which is very powerful. So if A and B are similar n by n matrices, then they have the same eigenvalues. It's got a cool little proof here. To start out, our premise is that A and B are similar matrices, right? So we can say since A and B are similar n by n matrices, there exists an invertible matrix P. And what am I going to say here? What's the definition of similar? Beautiful. Such that B is equal to P inverse times A times P. Good, good? All right, well, we're talking about eigenvalues. So the evil plan here is we want to show that these are going to have the same characteristic polynomial, right? So if we start off with checking out the eigenvalues for B, right? This would be lambda I minus B, and that's the determinant of lambda I minus B, right? But if we rewrite this and we replace B with P inverse AP, we'll have lambda I minus P inverse times A times P. And so that is due to substituting in P inverse AP for the matrix B. Groovy? All right, what do we know about any matrix? It is going to be similar to itself, right? As long as it meets the criteria. So I can write lambda I as, good, P inverse times lambda I times P minus P inverse times A times P. And that's because lambda I is similar to itself. Cool, cool? All right, so next up, well, what do you think? If we're a little bit creative here with our factoring, right? So if we were to look at factoring out a P inverse on the left and a P on the right, what would we end up with here? Well, we'd have lambda I, right? And then minus A. Wow, look at that. So, actually, let me make this closer. I didn't need so much room. Alrighty, well, okay. What can we do with determinants? Remember that the product of, or the determinant of a product of matrices is the product of the determinants, right? So we could write this as P inverse, determinant of P inverse times the determinant of lambda I minus A times the determinant of P. But now we're dealing with scalars. So I can move those scalars around, right? So I'll have the determinant of P inverse times the determinant of P times the determinant of lambda I minus A. Cool so far? But let's put the P inverse and P back together. So we'll have the determinant of P inverse times P times the determinant of lambda I minus A. But what is the product of P inverse times P? Beautiful. It's going to just be I, right? IN. So we'll have I, determinant of I times the determinant of lambda I minus A. And that's equal to, beautiful. The determinant of the identity matrix is just going to be 1, right? And that means we'll be left with the determinant of lambda I minus A. But what is that? Beautiful. This tells us that A and B have the same what? Beautiful. Have the same characteristic polynomial, right? Well, what does that mean? Thus, A and B have the same eigenvalues. Pretty cool little proof, huh? All right. And we're done. Let's take a look at an example. Okay? So, for this first example, we want to verify that A is diagonalizable by computing P inverse times A times P. And then B, we want to use the result of part A and that previous theorem to find the eigenvalues of A. So, let's check it out. What do we have to do first? Awesome. We need to find P inverse, right? Well, P inverse will be equal to 1 over the determinant of P, which is 3 minus 1, which would be 2. And then times, we'll switch the main diagonal entries and then put opposite signs on the non-main diagonals. So this, I'll just leave the 1/2 out for right now. So when I compute P inverse AP, what should I be getting? It should be a diagonal matrix, right? So hopefully that will work out. So I'll leave the 1/2 out for right now. So that gives us our P inverse, and then times A, and times P. All right, so continuing, we'll have 1/2 times, so I'll compute P inverse times A first off. So that's going to be what? 1 plus 1 is 2. And then 3 minus 5 is -2. And then -1 minus 3 is -4. And -3 plus 15 will give us 12. Groovy? And then we still need to multiply 3, 1, 1, 1. Well, why don't I go ahead and bring that 1/2 in, because I've got even numbers all throughout, so it'll make it easy. So this is going to be 1, -1, -2, and 6 times 3, 1, 1, 1. And that will give us 3 minus 1 is 2. 1 minus 1 is 0, looking good. -6 plus 6 is 0. And then -2 plus 6 is 4. Cool, cool? So that is a diagonal matrix. Let's call it D. So what did this theorem say? It says that if A and B are similar, they have the same eigenvalues, right? So All right, let's go ahead and use that theorem. So this, sorry, was part A. And then part B, we can say what? The eigenvalues of A are, well, what are the eigenvalues of this matrix D? 2 and 4, right? And A is similar to D, so the eigenvalues of A are 2 and 4. Pretty awesome, huh? All right, so we come to our next lovely theorem now. Condition for diagonalization. An n by n matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. Cool, cool? So the proof for this one's a little bit longer, but it's also a very, very cool proof here. So let's check it out. What's our premise? Don't we have 2 parts? So for part 1, what should we assume? Why don't we go ahead and assume A is diagonalizable. Good so far? So we're going to need to show that with that assumption, it follows that A has n linearly independent eigenvectors. Okay? So, what do we know? Well, if A is diagonalizable, there has to be a P, actually, an invertible matrix P, such that P inverse times A times P equal to, we'll call it D, is diagonal. Cool so far? All right, well, let's think about the column vectors, all right? Let's let the column vectors of P be, well, let's make it easy. How about P1, P2, all the way down to Pn, because remember A is n by n. And we also want to identify what? Well, we're dealing with a diagonal matrix, right? So we need to know the diagonal entries. So we'll let the entries on the main diagonal be lambda 1, lambda 2, all the way down to lambda n. Cool so far? Well, let's think about what we'll have. If we were to multiply the matrix P times our diagonal matrix, what are we going to have? We're going to have P1, P2, all the way down to Pn. And we're going to multiply this to our diagonal matrix, which will be lambda 1, 0, dot, 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 0, and then 0, lambda 2, 0, dot, 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 0. Let me move this one over a little. And we'll be going on in this fashion until we get down to lambda n. There'd be a 0 here, 0, 0, dot, 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 0, and then a 0 here. Cool, cool. So basically all the entries on the diagonal matrix are 0, except on the main diagonals. This is going to yield what? Well, P is a 1 by n, right? And we've got an n by n. So we're going to end up with a 1 by n. So we're going to end up with a 1 by n matrix for our result. And it'll just be lambda 1 times P1, lambda 2 times P2, all the way down to lambda n times the column vector Pn. Cool so far? All right. Now, since P inverse A times A times P is equal to this diagonal matrix, what do you think? It follows that, well, if I know P is invertible, so if I multiply both sides on the left by P, I'll end up with A times P is equal to what? Good. P times D, which is why we did P times D in the first place. Good so far? All right. This implies well, what would A times P be? Good. I'd have A times P1, A times P2, all the way down to A times Pn for the left for A times P. And I already showed that we'd have lambda 1 times P1, lambda 2 times P2, all the way down to lambda n times Pn on the other side. Groovy? All right, well, what do you think? Well, this means that API is equal to lambda I PI for each column vector P. Well, gosh, doesn't that sort of mean that the column vectors PI of P, the matrix P, are eigenvectors of A? Pretty amazing, huh? And also, since P is invertible, its column vectors are linearly independent. Isn't that cool? Therefore, A has n linearly independent eigenvectors. that's the close of the first part. Groovy? Okay, well, part 2. Now we have to go the other way because this was an if and only if proof. So let's now assume A has n linearly independent eigenvectors. And let's call them P1, P2, all the way down to Pn. And let's say that they have corresponding eigenvalues lambda 1, lambda 2, all the way down to lambda n. Cool so far? And let's also let P be the matrix which has these eigenvectors as its columns. Well, what will P be equal to then? Beautiful. P is going to be equal to P1, P2, all the way down to Pn. So since each of these column vectors Pi is an eigenvector of A, it follows that A times Pi is equal to what? Beautiful. Lambda I times Pi. Okay, so what are we going to have? Well, A times Pi will equal to A times P1, P2, all the way down to Pn, this matrix. Well, that's going to equal to lambda 1 P1, lambda 2 P2, all the way down to lambda n Pn, that matrix. Well, let's check it out. What would this product be? So starting down here again, I'm just rewriting this matrix. That's going to equal to what? What happens here? Well, isn't this just a diagonal matrix with all the lambda i's on the main diagonal? Cool. So you'd have lambda 1, 0, dot, 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 0, 0, lambda 2, 0, dot, 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 0, and then dot, 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 0, 0, dot, 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 0, dot, 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 0, all the way down to lambda n. Yes, there'd be a 0 in here. Okay, so prettying it up a little bit, we'd have this diagonal matrix. And that is equal to what? Beautiful. P times D. Since we know that P1, P2, all the way down to Pn, those column vectors are linearly independent, it follows that, what do we know about that? Beautiful, P is invertible. And we have what? A times P, right, is equal to P times D. Well, we know that P is invertible, so we can do what? We can multiply on the left side by P inverse. And then what? That gives us P inverse times A times P is equal to D. Groovy? Hence, A is diagonalizable. Okay. And we're done with that one. Our next example has our matrix A here. We want to find, if possible, a non-singular matrix P such that P inverse times A times P is diagonal. And then let's verify that P inverse AP is a diagonal matrix with the eigenvalues on the main diagonal. So let's check it out. What do we know about triangular matrices? Beautiful. We know that their eigenvalues are the values on the main diagonal. So we'll have lambda 1 is equal to 4, and lambda 2 is equal to 2, and it has a multiplicity of 2 because that root shows up twice. So if you're thinking of something graphically, that means it's tangent to the x-axis. It kisses the x-axis instead of crossing. All right? So, we also would be interested in knowing what is lambda times I minus A, and that's going to equal to lambda minus 4, 0, 0, negative 2, lambda minus 2, 0, and 0, negative 2, another lambda minus 2. Good, good? Well, we've got part of the problem done already. How nice. And let's continue. So 4I minus A times X equal to the 0 vector gives us what? So if we plug in 4 for lambda, we'll have 0, 0, 0, negative 2, 2, and 0, 0, negative 2, and 2, times our x vector equals to our 0 vector. Okay, well, let's check it out. If we take a look at 0, 0, 0, 0, negative 2, 2, 0, 0, and 0, negative 2, 2, and 0, well, what would we get for this? We'd end up with Beautiful. Negative 2x1 plus 2x2 is 0. And we'd have negative 2x2 plus 2x3 is 0. And this one would give us what? X1 would equal to x2, right? And what else? X2 would equal to x3, right? And that would make x1 also equal to x3. So our first eigenvector, x1, will be equal to x1, x2, x3, which in turn would equal to, if we parameterize, what would we have? T, T, and T. And if we were to factor out that T, we would have 1, 1, and 1. So I just basically let x3 equal to T. All right? Now, what we're interested in is we're interested in a basis for this. So a basis for the eigenvector corresponding to lambda 1 equal to 4 is 1, 1, and 1. Groovy? Okay, let's work with lambda 2 equal to 2. So now, I'll do this in a different color. We would have 2 times I minus a times the x vector equals the 0 vector. So that's going to give us, let's see, 2 minus 4. So 2 minus 4 is, so we'll have negative 2, 0, 0, negative 2, and then 2 minus 2 will 0 out. So then we'll have this matrix times the x matrix equals to the 0 matrix. Groovy? All right, so I don't know, let's check it out. Let's do it. We would be solving, or reducing this augmented matrix. So we'd have negative 2, 0, 0, 0, negative 2, 0, 0, 0, and then 0, negative 2, 0, 0. Okay, well, what are we going to have? We know that if we do negative row 1 plus row 2 for a new row 2, we'll end up with 0, 0, 0, 0 for row 2. Which in turn gives us negative 2x1 equals 0. And then negative 2x2 is equal to 0. And then we've got the free variable for x3, right? So we'll let x3 equal to t. This one, of course, gives us x1 is 0. This gives us x2 is 0. And then we have x3 is t. So what do we have? Our x2 vector is what? Well, you'd have x1, x2, and x3, which would give us 0, 0, and t, right? And that in turn is going to give us t times 0, 0, 1. But you know what? We're only going to get 2 eigenvectors, right? So a basis for the eigenvector corresponding to lambda 2 equal to 2 is 0, 0, 1, right? Well, what would we conclude for this problem? How many eigenvectors do we have? Good. 2. Since we only have 2 eigenvectors, and the dimension of our space, remember we're in R3, is 3, A is not diagonalizable. And I should have said linearly independent eigenvectors. Cool, cool? So we're done with this problem. All right, so let's look at steps for diagonalizing a square matrix. Let's let A be an n by n matrix. First off, what do? We find n linearly independent eigenvectors, P1, P2, all the way down to Pn. So you do that by finding a basis, right, for the space, all right, with corresponding eigenvalues, lambda 1, lambda 2, all the way down to lambda n. If n linearly independent eigenvectors do not exist, then A is not diagonalizable. Now don't confuse eigenvalues with eigenvectors. It has to be n linearly independent eigenvectors. So then you let P be the n by n matrix whose columns consist of these eigenvectors. So P will equal to P1, P2, all the way down to Pn. And you find these, so this would have been each of these bases, so 1, 1, 1 would have been P1 if this had been diagonalizable. 0, 0, 1, let me circle these, 1, 1, 1 would have been like our P1. 0, 0, 1 would have been our P2 had this been diagonalizable, okay? All right, so then the diagonal matrix D equal to P inverse times A times P will have the eigenvalues, what? Beautiful. Lambda 1, lambda 2, dot, 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 lambda n on its main diagonal, and of course zeros elsewhere. Note that the order of eigenvectors used to form P will determine the order in which the eigenvalues appear on the main diagonal of D. Okay? All right, now be careful with this next theorem. It's called a sufficient condition for diagonalization. But notice it's not an if and only if proof, so it only goes one direction. So if an n by n matrix has n distinct eigenvalues, then the corresponding eigenvectors are linearly independent and A is diagonalizable. But it doesn't go the other way, all right? So if you do not have distinct eigenvalues, you might still have a diagonalizable matrix. Okay? But if you have n distinct eigenvalues, you know for sure that you will. So let's take a look at this proof. Why don't we let lambda 1, lambda 2, all the way down to lambda n. And our premise here is what? That they are n distinct eigenvalues. Of A. And then we need corresponding eigenvectors. And why don't we call these corresponding eigenvectors x1, x2, all the way down to xn. Good so far? Why don't we suppose this set of eigenvectors is linearly dependent. Let's also further suppose that the first m eigenvectors are linearly independent and the first m plus 1 eigenvectors are linearly dependent. We're also going to let m be less than n. Cool so far? So what we're going to do is try to set up a contradiction, as you can see. So if all this stuff, were true, these further supposed things, then couldn't we write x sub m plus 1, so the m plus first eigenvector, we could write that as a linear combination of the linearly independent eigenvectors, right? So let's do it. We would have c1, x1 plus c2, x2, all the way down to cm, xm. Cool so far? Let's name this equation. This will get a little messy maybe. So we'll call this one equation 1. Where not all CI's are 0. Cool so far? All right, well, let's think about what if we multiplied both sides by a, right? So if we had a times x sub m plus 1 equal to a times all of these sums, of vectors times their constants, what would we have? We'd end up with a c1 x1, right? Plus a c2 x2, all the way down to a cm xm. Good so far? But we know from our premise that A has n distinct eigenvalues, right? And so we had let lambda 1 all the way down to lambda n be these n distinct eigenvalues of A. So that tells us what? Well, it tells us that A times xi has to be equal to what? Lambda I times xi for I equal 1, 2, ... all the way down to m plus 1. So we have lambda m plus 1 times x m plus 1 on the left, and that's going to equal to what? Beautiful. C1 times lambda 1 x1 plus C2 times lambda 2 x2 all the way down to Cm times lambda m xm. All right, well, let's call this one equation 2. All right, the next step we're going to do is we're going to multiply equation 1 by lambda m plus 1. All right? So what are we going to get? We're going to get lambda m plus 1 times x m plus 1 is equal to lambda m plus 1 times c1 x1 plus lambda m plus 1 times c2 x2 plus all the way down to plus lambda m plus 1 times cm xm. Okay, so far? Now this one we're going to call equation 3. Our next step is going to be to subtract equation 2 from equation 3. I'll go ahead and rewrite them. So this would be, cool so far? All right. Well, what will we get on the left side? Beautiful. We'll get the 0 vector on the left side. And on the right side, what's going to happen? We'll have, well, let's see what we have in common. Do you see we'll have the CI's in common, and we'll have the XI's in common. So I'm going to factor out a C1 on the left, and then we'll factor out the X1 on the right. And what's going to be happening? We'll have lambda m plus 1 minus lambda 1 times the vector x1. Cool so far? And then plus C2 times lambda m plus 1 minus lambda 2 times the vector x2. And then it'll continue it in that manner till we get to Cm times lambda m plus 1 minus lambda m times xm. Cool, cool? All right then. Well, we assumed our own assumption, right? Not the premise. We assumed that the first m eigenvectors were linearly independent. So now that we have the 0 vector on the left side, what would have to be true? Beautiful. This would mean that C1 times lambda m plus 1 minus lambda 1 would have to equal to 0. C2 times lambda m plus 1 minus lambda 2 would have to equal to 0, all the way down to Cm times lambda m plus 1 minus lambda m would have to equal to 0. But, okay, what do we know about the eigenvectors? The eigenvectors are all distinct, right? And so we know for sure that C1 equals 0, C2 equals 0, all the way down to Cm equals 0. And we know this since x1, x2, all the way down to xm are distinct. Well, but if that's true, wouldn't it contradict our assumption that x sub m plus 1 can be written as a linear combination of the first m eigenvectors. Thus, the set of eigenvectors is linearly independent. Therefore, from our earlier theorem, what? A is diagonalizable. And that was from which theorem here? Oops, sorry. It was from theorem 4.21. And we're done. All right, that's always a nice proof. Okay, so let's take a look at example 3. Find the eigenvalues of the matrix and determine whether there is a sufficient number to guarantee that the matrix is diagonalizable. So here, now be careful, again, that it was a one-way proof, right? So with this one, lambda 1 equals 2 equals lambda 2, right? So there exists only one distinct eigenvalue. In a two-dimensional, right, space. Since we're in R2. So, we cannot guarantee that this matrix 2052 is diagonalizable. We'd have to go through the process to see if it had n linearly independent eigenvectors. So it might be, but we can't guarantee. All right? Example 4. Find a basis B for the domain of T such that the matrix for T relative to B is diagonal. So T is going from R3 to R3, where T at x, y, z is equal to negative 2x plus 2y minus 3z, 2x plus y minus 6z, and negative x minus 2y. All right, so this is kind of putting together lots of stuff here. So our first step is to do what? We need to find A, which is the standard matrix for our transformation. Cool, cool? So, how did we do that? Beautiful. We needed to find the linear transformation at E1, E2, and E3, the standard basis vectors for R3, right? So let's do it. T at 1, 0, 0 is equal to what? Let's see, we'll get negative 2, 2, and negative 1. And then T at 0, 1, 0 is 2, 1, and negative 2. And then T at 0, 0, 1 is equal to negative 3, negative 6, and 0. Groovy? All right, well, what does that mean? That means that A is made up of the vectors we found written as column vectors, right? So going down, we have negative 2, 2, negative 1. And then 2, 1, negative 2, and negative 3, negative 6, and 0. All right. Since our goal is to find a basis B for the input, the domain of T, so we get a diagonal matrix, what does that mean? We had diagonal matrix in there, so we need to find the eigenvalues. Very good. So our second step is we need to find the eigenvectors of A. Okay? Well, remember, finding the eigenvectors, we have to do a few things, right? So we need what? We need to know what is lambda I minus A, right? So that would be lambda plus 2, negative 2, and positive 3, negative 2, lambda minus 1, and positive 6, positive 1, positive 2, and lambda. Groovy? Our x vector, right, is just going to be, we're in 3 by 3 land, so we'd have x1, x2, and x3. So let's start off by, we're going to find the eigenvalues of A. Okay? And so remember, what do we have to solve? Good. We have to set the determinant of lambda I minus A equal to the scalar 0. So to do so, let's see, what do you want to expand about? It doesn't really matter. Why don't we just do plus, minus, plus. That'll be easy enough. All right? So here we go. This will be lambda plus 2 times the determinant of lambda minus 1, 6, 2, and lambda, minus a negative 2. So we'll have plus 2 times the determinant of negative 2, 3, and 2 lambda, plus 1 times the determinant of negative 2, 3, lambda minus 1, and 6. And we have to set this all equal to 0. Cool, cool? All right, so working it out, we'll have lambda plus 2 times lambda minus 1 minus 12 plus 2 times negative 2 lambda minus 6, and then plus negative 12 minus 3 times lambda minus 1. That's all equal to 0. So I'm going to go ahead and do the algebra here quietly, and you can go ahead and try doing it on your own. And let's check it out. So as you can see, the solutions to this equation right here at negative 3, we have a 0. And this is kissing the x-axis. It's tangent to the x-axis. So this would be lambda is equal to negative 3, and that's going to have a multiplicity of 2 because we have a third degree polynomial, and so we need to have 3 roots. So that has multiplicity 2. This here is 5, 0, all right? And so this is lambda equals 5, and that just has multiplicity of 1. Cool so far? Okay. So now we need to find our eigenvectors, right? We'll call this part B. So let's go ahead and look at lambda 1. Call this 1 and 2. So lambda 1 equal to negative 3. We'll have negative 3i minus a times our x vector equal to the 0 vector. And that's going to give us what? So I'm coming back to this lambda I minus a to get this following matrix. And it follows that we'll have -1, -2, 3, -2, -4, 6, and 1, 2, and -3, multiplied to our x vector, which was x1, x2, x3, equals our 0 vector. Row reducing this one, let's see what we'll get. So the reduced row echelon form of this matrix ends up being 1, 2, -3, 0, and then the other two rows are 0. And what does this tell us? This tells us that x1 plus 2x2 minus 3x3 is 0. Isolating x1, we'd get -2x2 plus 3x3. And so if I let x2 equal to s and x3 equal to t, x1 would equal to -2s plus 3t. And so our first eigenvector will be, or eigenspace corresponding to the eigenvalue lambda 1 equals -3 will be, so we have our x1, x2, and x3, but that's equal to -2s plus 3t, s and t. And notice we have two parameters. So we'll get s times -210 plus t times 301. And if we let s and t equal to 1, a basis for the eigenspace corresponding to lambda 1 equal to -3 is this set here. So we'd have -210 and 301. And so we found vector P1 and vector P2. Cool so far? All right. All right, so now for lambda 2 equal to 5, well, 5i minus a times x equal to the 0 vector is, so again, we're coming back to the vector circled here. And when I plug 5 in for lambda, I'll get this matrix. 7, -2, 3, -2, 4, and 6, and 1, 2 times our x vector equals to the 0 vector. All right, so we need to find the reduced row echelon form of this augmented matrix I'm writing here. And let's check out what the reduced row echelon form is. So this gives us x1 plus x3 is 0. x2 plus 2x3 is 0. So x1 equals negative x3, and if x3 is t, that would give us negative t. And x2 would be equal to negative 2x3, so negative 2t. So our x2 vector is equal to x1, x2, x3, which will be negative t, negative 2t, and t. And if I bring the t outside, I'll have negative 1, negative 2, and 1. Cool so far? And a basis for the eigenspace corresponding to lambda 2 equals 5 is letting t equal to 1. So we'll have negative 1, negative 2, and 1. And this becomes our P3. Groovy? All right. So next up, we have our P. So putting it all together. All right, so what we found here is we found our P matrix, remember, is P1, P2, and P3, which is equal to, we had P1 and P2 are right here, so negative 2, 1, 0, 3, 0, 1. And then P3 is here. So using the calculator to find our diagonal matrix, which you probably already know what it is, but we're checking to make sure. What do we know? This is going to have the same eigenvalues, and it'll be diagonal, right? We know D equals to P inverse AP. And so if we did everything right, we should get negative 3, and 5 along the main diagonal, and 0s elsewhere. And we want to check that and make sure it's true, okay? So let's go back to the calculator and see what we got. So let's clear all this, and we're going to need to enter in A, P, and we can find P inverse using the calculator. So let's do it. I'll let B equal to our P matrix. So our P matrix was. All right, so now we want to find P inverse times A times P. Well, in this case, it'll be B inverse times A times B. That'll be our diagonal. So, matrix B, and I need to inverse that, times second matrix A times second matrix B. Drum roll. And look at that. We get our diagonal matrix. Isn't that cool? That brings us to the end of today's lesson, and I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, please subscribe. Bye.